very small as compared to the MTech syllabus. So I'll just teach whatever is relevant to you as per your curriculum. Okay. Mostly you can focus on the slide. That's more important than focusing on because I'm just speaking. Full slide is coming.
Yeah.
Okay. So if at all I wanted to show my face, I'll come here and then.
Okay, fine.
So people should know I am taking class. So, okay. There are many force measuring devices available, sensors available. Out of that, few of them normally we teach in the class. But as per your syllabus, there are only specific devices only they have mentioned because your control system syllabus is vast. People wanted to give more focus on control system side. They wanted to reduce the number of devices that you study on instrumentation side. So I will just focus on whatever is there in your syllabus. I give pointers to the other sensors that you can study from. Some of my own recorded lectures which I have delivered for MTech students available in YouTube. If you want, you can go through. Or there are very good lectures from IIT Madras Professor Dr. Professor Raman. He has given mechanical measurements. That's the NPTEL, National Program on Technology Enabled Learning. They have given very good lectures. There are also other electrical professors from other IITs. They have given, very good treatment on other transducers, not only for pressure measurement or force measurement, for variety of measurement devices. Okay? So I'll be focusing only on what is there in your syllabus, and of course it will be not much introduction. Normally we spend a lot of time on defining what is force, defining what is pressure. Those lectures probably I will share it with you through WhatsApp. I'll send you the YouTube link. You go through. Because of want of time, I wanted to complete the third unit also to the greater extent possible. Second unit we have completed yesterday. Only gyroscope we have not covered. That is self-study. You will study by yourself. The working principle of gyroscope. Okay? Accelerometer we have taught. LVDT yesterday we have finished. I think with that second unit completely we have covered, except one topic, gyroscope. Third unit is also there for your syllabus. I have taken the question paper, handed over to the exam hall. So whatever we teach, that is also equally important. Okay? Whatever we taught yesterday, that is also important. So you should not miss anything which is taught in the last moment. Doesn't mean first few classes are useless. That is also useful, but this will be more useful. So pay more attention. Now, force and torque measurement using strain gauge. That is the very specific topic that given in the syllabus. So, using strain gauge, how to measure force, how to measure torque. That is what you should learn. For measuring a strain, first we should know how to measure the strain. Then only we will be able to measure force and torque. So, to measure strain, we need to know the working principle of the Wheatstone bridge. Yesterday, I think she has given an overview. I also requested you to go through the fundamentals of Wheatstone bridge. I hope all of you know the working of Wheatstone bridge, isn't it? Okay. So if you have a bridge like this, supposed to be a resistance. Huh? And here you have a galvanometer connected, and of course here plus and minus power supply is given. The naming is very important. See, the R1, R2, R3, R4. Suppose you give R1, R2, R3, R4, R1, R2, R3, R4, the relation slightly will change. Okay? Because it's all derived from first principles based on the initial condition. This is the initial condition. I start from here in the clockwise direction. I have given the names. For this bridge, of course, there is a balance equation which she has described yesterday, and unbalanced voltage E naught is equal to E divided by 4 into delta R1 by R1 minus delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4. So R1, R2, R3, R4 are the resistances in the Wheatstone bridge respectively. People were here not able to see. and delta R1 is change in resistance 1 because of the measurement. In place of resistance, we put a strain gauge. This will be replaced with strain gauge. SG means strain gauge. We put a strain gauge. Then, if you put a normal fixed resistance, there won't be change in the resistance. If you put a strain gauge, as the elongation takes place in the strain gauge, there will be a change in resistance. Okay, because the strain gauge will look something like this. Now, I'll erase it. It will look something like this. And this is the axial direction. When the strain takes place, the length changes. The resistance is given by rho into L by A, where rho is resistivity of the material. Okay, so that's more or less fixed, assuming you are having the room temperature and many other parameters constant, like what we have at the room. We say resistivity is constant for most of the practical purposes. Okay, it will change, but the change is very small, so we assume it to be constant for our engineering measure. And L is the length. See, this is the length. The length of the wire goes like this, goes like this, goes like this. This becomes length. A is the cross-section area. You cut here, there will be a small cross-section area that you see. That's the area. When the length is increasing like this, there won't be much variation in the cross-section area. Of course, there will be reduction in the cross-section area. It is not very appreciable. Whereas, since the length is more, when the strain takes place in this direction, the length, the delta L is very high compared to delta A and delta rho. So, for simple explanation, we assume the A is more or less constant, rho is more or less constant, and whenever there is a strain, there is a change in length. And whenever there is a change in length, proportional to that, there is a change in the resistance. So, this is the working principle of strain gauge. And whenever there is a change in the resistance, this resistance will change. Suppose if you have connected strain gauge here. Here also you have replaced this with the strain gauge. Here also you have replaced with the strain gauge. And so here, so there is a possibility of change in R1, change in R2, change in R3 and change in R4. So delta R1, delta R2, delta R3, delta R4 are basically the changes in the respective resistance values. Okay, and suppose if there is a change in R1, R2, R3, R4, what will be the unbalanced voltage? When the bridge is balanced, yesterday Mitali has given an expression if for the balance of Wheatstone bridge. At that condition, unbalanced voltage in the galvanometer, what you read is 0. Okay. Now let's say this is positive and negative. This is capital E. Capital E is the excitation voltage, whatever you are given. You are given a 9 volt battery if you are connected. Capital E is 9 volt. So that's the excitation voltage. Whatever the voltage you get, you connect. During balanced condition, then galvanometer reading will be 0. There is no current flowing through from this point to this point because the potential here will be same. Both places voltage will be same. It's a parallel path. Same resistance here, then only you will get a two parallel path. If there are two parallel paths with the same potential, there won't be any cross flow. Isn't it? Flow will take place only there is a potential difference. When there is a temperature difference, the heat will flow. When there is a voltage difference, current will flow. When there is a pressure difference, the liquid will flow or fluid will flow. So there should be a potential difference for flow to take place. Here there is no. Here also same potential. Here also same potential. At balanced condition, here you will have no potential, no reading, 0. Okay, that's a null balanced condition or perfect 0 condition. That's the starting point of our measurement. We put strain gauges. Even if there are minor changes in the initial resistance of these values, normally commercially available strain gauge will be 120 ohm strain gauge, 240 ohm strain gauge, 360 ohm strain gauge. They are all standard values available in the market. You go and ask for a strain gauge, they will ask what kind of strain gauge. Lot of shapes are available. Forget about the complications or shape of the strain gauge. Normal strip type strain gauge like that if you take, they'll ask for what is the ohm that you want, how many ohms you want. You say 360 ohm strain gauge you give you, they will give you the 360 ohm strain gauge. So they will have initial values. due to manufacturing variation, it is not, if you buy 5 strain gauges, all 5 may not be having exactly 360 ohm resistance. There are minor variations. Okay. So if there are minor variations in any one arm or any two arms, you put the variable resistance. Purposely, you put a part. What is the voltage E naught is given by capital E, that's the supply voltage, divided by 4 into this delta R1 by R1 minus delta R2 by R2 plus delta R3 by R3 and minus delta R4 by R4. So it is in the clockwise direction, alternate signs, plus and minus alternate signs are okay. Now we will hold this equation. We also call it as 1 ohm condition, 2 ohm condition, full 4 ohm condition, or we say quarter bridge, half bridge, and full bridge. What is meant by quarter bridge? I replace only R1 with the strain gauge. Rest are all fixed resistances. Okay, there is no strain gauge. That time there won't be any variation in R2. There won't be any change in the R3. There won't be any change in the R4. So delta R2 0, delta R3 0, delta R4 0, these terms vanishes. These terms vanish. Here you have delta R1 by R1 into E divided by 4, that will be the unbalanced voltage that you get. Okay, that's okay, there is no complication there. There is no trick that you can really use in single arm bridge. When it becomes double arm, 2 ohm bridge or half bridge, there is you have a possibility of using the same bridge in 2 different ways that you should learn. Suppose I have 2 strain gauges. Either you can connect R1 and R2, or you can connect it in R1 and R3, or you can connect R1 and R4. So, any 2 combination, any 2 you can connect, isn't it? Simply we have given some name R1, R2, R3, R4, but there are 2 places randomly you can connect anywhere. Okay. Now look at here. Some people may not be able to see. You're able to see. Okay. Now look at here. Suppose I connect between R1 and R2. Here I have one strain gauge, here I have one strain gauge. You will see that there is a change in resistance here divided by its original resistance. There is a minus sign. And the second arm, there is a change in resistance. If I say initial resistance is same, R1 equal to R2 equal to R3 equal to R4, all initial resistance are same. Let us say 360 ohm. I bought 360 ohm strain gauge, all are exactly 360 ohm, and I put that. So R1 also 360, this also 360. So that becomes a common denominator, isn't it? And on top, what happens? One quantity is getting subtracted from the other quantity. If I connect in R1 and R2. Same thing, look at here, R1 and R3. Suppose I connect strain gauges in R1 and R3. Here R1, delta R1. Here there is a plus sign. Of course, delta R2 will be 0 because we have not connected a strain gauge. Here it is only fixed resistance, no change in resistance. Delta R2 0, delta R4 0. So this term vanishes, this term vanishes. These 2 terms vanish. Here you have, let's say this is also 360, this is also 360. There is a delta R1 plus delta R3. If I connect it in R1 and R3, the change in resistance is getting added. If I connect it in R1 and R2, the resistances are getting subtracted from one from the other. So you should know where to connect the strain gauge when you are making a measurement. If you are interested in subtracting certain things, then you should look for R1 and R3, or R3 and R4. Anything. So you look at the term, algebraically you should connect it accordingly. Is that clear to you? Okay, if you want to add 2 resistances, 2 change in resistances, then either R1 and R3 or R2 and R4. Of course, negative sign is simply a sign, but as long as resistance, they get added. Okay? Minus R2, minus R4, so they get added. Only thing, let's say instead of 3.2 volt, you will get minus 3.2 volt. There is a negation sign will be there. You can ignore that sign and then take only the magnitude. If the sign is important, then of course you have to go to R1 and R2. So you should master this technique so that you will be able to use strain gauge measurement for the purpose of force measurement or pressure measurement or torque. Up to this is clear to all of you? Any questions?
The negative sense.
Yeah.
I got it.
Oh. Laptop. Load cell is a word used for the sensors used to represent the sensors used for measuring force. Okay, load cell. Load means force. And here, column type strain gauge. This is the column type strain gauge. What we normally do is we take an elastic member, reduce its cross section area. Okay, why we reduce the cross section area? Why we take reduce the cross section area? We take a circular shaft and reduce the cross section area to the thin value. Why we do the thinning operation?
Reduce resistance.
So that
The resistance can be reduced.
Not resistance.
Increase.
Huh? It's a mechanical idea. There's nothing electrical about it.
Stress is more.
Huh?
Stress is more.
Stress?
Is more.
Stress is more, so strain is more, isn't it? To induce stress concentration. You heard about stress concentration? Forget about the technical term. You have, let's say, you have a linkage, you have a chain, okay, made up of links, and you pull it with force. Which link will fail first? The link which is need not be in the center. Why near to the center? It can be close to your right hand, it can be close to your left hand. It need not be in the center. If you have a chain made up of links, which link will fail when you apply force? The link which has less cross section. It's a common sense. There is nothing engineering in that. The weakest link will fail first, isn't it? The weakest link will fail first. It need not be in the center. If all the links are of same strength, then probably the middle link will fail first. Middle link will fail first. So if the cross section area is maintained constant throughout, it can fail anywhere. Okay, wherever the weakest, some small crack or initiation, small manufacturing defect is there, small hairline crack is there, crack will initiate from there and failure will happen because of that. We don't want such thing. We want the entire force to act and effect on somewhere here. We want to direct the effect of the force towards in the middle. So what we did, we reduced the cross section area. That means what? We made that area as weakest part. That's the weakest. If it is breaking, it should break there. If it is elongating, it should elongate there. Okay? So if you apply compressive force, even tensile force, whatever is the extension takes place or contraction takes place, that will be somewhere here. Okay? So the reduced cross section area is to increase the stress concentration. So all the force that you apply will be acting upon this small area, so the stress is more here. What is stress? Force divided by area. Same amount of force will be acting over the big area, so the stress concentration is less. Same force will be acting over this small area. A force divided by smaller area, you have higher stress. So its stress concentration is high. So high stress it is subjected to, so there will be high strain. More strain will be there. Proportional to stress, there will be strain. So here we induce stress concentration by reducing the cross section area and make the workpiece elongate proportional to the stress. That's the material property. Stress is directly proportional to strain within elastic limit. Hooke's law, isn't it? You might have studied. It's not the material, right? So here you have the straining action. What we do, we put one strain gauge along the direction of strain. See, one is along the direction of strain. and opposite face, not 2, the 3 which is on the back side of this, we have one more. So 1 and 3 we will connect it to resistance 1 and resistance 3. Why? Those two strain gauges will increase in resistance when there is a tensile force. Those two strain gauges will reduce in resistance when compressive force. Length will reduce and resistance will reduce, and so. So this strain action is proportional to the amount of force that is applied. So force is applied on the elastic element, the strain takes place in the elastic element, and the strain gauge is pasted. Because of the change in the length, there is a change in the resistance in the strain gauges 1 and 3, and 1 and 3 is connected to 1 and 3 in the strain gauge Wheatstone bridge. That's connected to the bridge circuit. CKT means short form of circuit. Okay? So I have used just acronym. It's not a standard acronym, but you should understand. And here it's an error. We are interested only in change in resistance because of the force, because we are measuring the force. We assume all the change in resistance are because of the change in the force. Any change in the resistance which is not because of the force is an error as far as we are concerned. Okay, so the temperature which causes this temperature difference that causes this strain, that's called thermal strain, is an error to us. We wanted to eradicate that, remove that as much as possible, if not fully, at least to the extent possible. So what we do, I put another strain gauge here, okay, other strain gauge here, and the material will elongate in axial direction because of the force, or if it is compressive force, compressive force. Both extension and contraction will take place only in axial direction. You know what is meant by axial direction? This is axial direction. There will be a small increase or decrease in the cross section area. If it is elongation takes place in the axial direction, there will be a contraction in the cross section. If there is a compression that is taking place in the axial direction, there will be increase in the cross section. Isn't it? Yes or no? Okay. But other than that, because of thermal expansion is not direction specific. It's not happening only in one direction. It takes place in all directions. If you heat the material, it expands in all the three directions equally. Not that x-axis alone it expands, y-axis it is not expanding. It's not because of that. Only for force it is directional specific, because force is applied on one specific direction. When due to temperature difference, the thermal expansion takes place in all three directions. So what I do, I wanted to reduce the error, not nullify. No, reduce the error because of the thermal expansion. So what I do, I simply put one strain gauge in this direction. This strain gauge is looking like a strip, but if you magnify, it will be like a grid, wire grid, that which I have drawn and shown somewhere here. Okay, so the strain gauge here, when elongation is happening or compression is happening, there won't be much change in resistance in these strain gauges. Whereas elongation takes place, that directly affects this. The length changes drastically, and there is a great change in the resistance. If at all there is a change in resistance value, appreciable resistance, change in resistance value in 3 and 4. No, 1, 2, yeah. 1 and 3, 2 and 4. Okay, 2 and 4. If there is a change in the resistance value, that is mainly due to change in temperature. That's mainly due to change in temperature. Anybody is not able to follow that? Okay.
Which one is one here?
This face is 1. This is 1. The adjacent side visible to you is 2. Back side of 1, which is not visible to you, is 3. Back side of 2, which is not visible to you, is 4. Drawing ஏன்டா படிச்சீங்க? See, it kept like this. It's kept like this. This is 1. This is 2. Both you are able to see. This is 3. This is 2.
So, but when like if a rod expands, there would be some change in its diameter because volume would remain constant, so cross section area would decrease.
Yeah, there will be reduction.
So that way our horizontal strain gauge have to be calibrated.
Small shrinkage will be there. Small shrinkage will be there. Yeah. That is why we tell the error due to temperature is not completely rectified. You look at this change in resistance. You look at that change in resistance. Take only R1. Okay. R1. What are the changes? There is a change in R1 because of the force that we apply. Because of the force that we and time being, let's assume we are applying a tensile force and the length is increasing. So delta R1 will be positive. Okay, so it's positive. Put positive. And in the strain gauge 1 itself, because there is a small cross section reduction, there will be a small reduction in the delta R1 because of the cross section reduced, length increased in the longitudinal direction that I put because of here. Okay. Now there is another change in the same resistance 1 because of cross section area, and that will be minus reduction. Okay. Due to temperature variance, suppose you are calibrated at 23 degrees Celsius and now you are using it at a higher temperature. Because of more temperature, there will be elongation, expansion. You are calibrated at 23 degrees Celsius. Suppose you are using it in London right now. London temperature is minus 2 degree, minus 1 degree Celsius there. You calibrated at 21, using at a lower temperature, there will be a contraction. Depending upon temperature, there will be one more change in resistance in the same R1 because of temperature. That may be positive or negative. Let's assume India condition, we referred 23 degree standard we calibrated. Right now it is more than 23 degrees Celsius, so it's positive. All these three will be responsible for change in R1. All these three are responsible for change in R1. Look at R2. What's happening to change in resistance R2? R2, because of the tensile force, there will be a small change in resistance. Okay, not as high as here. This is big. This is a big quantity. This is a big quantity. This is a small quantity. Of course, this is error. That also will be small generally, but that's our error. We are interested in nullifying or reducing. Look at R2. That's again, there is a change in R2 because of the force that is applied. That's generally negative in direction because reducing action takes place. There is a length increase in here, isn't it? Because the tensile action, the strain gauge plays axially. The strain gauge is like this. Okay. Here the length will increase a bit. Okay, bit. But here and all nothing will happen. The main length does not affect. But small length here, small length here, small length here, small length here, there will be an increase in very small quantity. R2 because of cross section changes. I'm talking about the strain gauge. Of course, there will be a change in the R2 because of temperature also. This is again error. This will be same positive error, and this is error. Same error will be there. This and this will be almost same. 5 ohm error there, here also 5 ohm error. This will be like 0.1 ohm, 0.1 ohm, like a very small in quantity, almost negligible. That is why for a detailed discussion we can take this. Of course, this will be positive, and or for a preliminary discussion we can ignore this because this is a very small quantity. In a total change in R1, this may not have big effect. This will be like 10 ohm, 15 ohm, things like that. This will be like 3 ohm, 2 ohm, which adds error to it. This will be 0.1 ohm, zero point 0.2 ohm. So you don't mind coins when you are dealing with 100 rupees, 200 rupees, right? 1 rupee coin, not 1000 rupee coin, but 5 paise coin, 15 paise coins, and small coins. You don't mind when you are having big currencies. That way, for engineering consideration, these small quantities I have ignored. Otherwise, that also will affect the change in resistance. Now, what we do? This is a positive quantity. This is a negative quantity, and I wanted to cancel off this error. Okay. So what I will do? R1 I have connected to R1. This resistance, let me not name it, whether it is R2 or R3. Another strain gauge which I have connected here. I wanted to subtract. Why? When I am subtracting, I get this is a big quantity, this is a small quantity again, this is a small quantity, this is a error quantity. This will slightly affect the actual value that we get there. Doesn't matter. So what I do is R1 is here, R2 is here. When I connect this to R1, this to R2, what happens? This gets subtracted. When this gets subtracted, what happens? The total resistance will be delta R1 force minus of minus is plus delta R2F, okay, and this we have ignored. Even if you are taken into consideration, this minus this both are minus quantity, minus of these two cross-sectional effects will come, but that will be very fractional, so we ignore it. Here both are same quantity, both are positive initially, but I am subtracting this from this, so what will happen? Okay, these two are same quantity. One is subtracted from other. The error is almost reduced to zero, but in the process I am introducing another one. So this will add error to the actual measurement. This is what we are interested in. What is the change in resistance in R1 because of the force? In doing so, this is called temperature compensation. This is called temperature compensation. Temperature compensation. Okay, so I am eliminating the error because of temperature, but in the process I am introducing another error, which is that this is the axial deformation. This is the cross-sectional deformation. That will be very minimal, but still I am introducing that error. That's why I am saying error cannot be fully nullified. Nullified means completely removed, but we have reduced the error. If you incorporate this, the error in the reading will be more, whereas this, the error is less. That's why people don't mind adding this to the error signal. In fact, along with this, they calibrate while doing calibration so that your reading is much better. Whereas this, you cannot do calibration in the laboratory. You cannot club those two and do a calibration. Why? The temperature here and the actual place of measurement will be different. We don't know where we are using. Suppose you are doing a strain measurement near a furnace, the temperature will be 40-45 degrees Celsius. In an AC room in the laboratory, same instrument we do it, it will be 25 degree, 24 degree, 23 degree, depending upon what temperature we set. So since that cannot be predicted, people club this also along with this. This as a unit they calibrate to find out what is the shown force value. So whatever is the force or the torque that you are measuring in the instrument, the combined value of these two, calibrate along with it, so that you will get. The easiest way, if there is no temperature problem, the easiest way is take only R1, connect it to R1, take the measurement. The sensitivity is not sufficient. The change in resistance is 10 ohm. Proportional to that, some 0.5 volt, 0.2 volt. Very difficult to do signal processing if the voltage is very small. Okay, you should get more voltage because of more change in resistance. Then only you can do signal processing easily. So that is why we take R1, also R3. Put one more on the back side of R1. R1 and R3. Connect it in R1 and R3. So that now there is a higher change in resistance that you are getting for the strain strand. Proportional to delta R is more, delta V is also more. Voltage changes also more. So you will be able to measure a good amplified voltage. This is temperature compensation in strain measurement, and also it is applicable for force. Any questions? Force measurement using strain gauge loads. Any questions? Doubts? Straight off. Of course, advantage, disadvantage. I'll just quickly browse through so that you know the many of the force measuring devices like normal spring balance or a normal physical balance, what you see in the physics laboratories, all that may not give an electrical output, whereas load cell gives an electrical output. That's a big advantage. Many of the force measuring devices will not give an electrical output. Even you go to weighing bridges that you see, that's also force measurement only basically. Weight and force are same. Weight, load, force, they are all same. So weighing bridge you go, the olden type weighing bridges you see a box-like structure, and there is a needle of my hand arm length which will show you the actual load. Up to 20 tons, up to 30 tons. They write the capacity also on top of the weighing bridges you might have seen. It does not have electrical output. There is a spring element, and there is a movement according to the weight or the force, and that is transferred into a circular movement, and you measure the weight or force using mechanical movements, no electrical output. Recent weighing bridges, of course, they put the strain gauge and then take the output, they get electrical output. So load cells are the ones which gives electrical output, and that's a big advantage. Small in size, and you also price is also reasonably less. It can measure deflections up to 0.25 mm. This is 5 years back data. New developments may be there. Maintenance is almost nil because it's very rugged instrument and good dynamic response. What do you mean by dynamic response? However fast I apply load and remove, the sensor will be able to respond. That's a dynamic response. Okay. Slowly, for example, if I put the load, take thermometer, dynamic response is very poor. Why? I put thermometer on my mouth. To get the actual temperature of my body, I have to wait for 30 seconds to 1 minute. You might have seen doctors or nurse taking reading from our body. That's because the dynamic response is very less. It takes long time to respond and to show the actual reading. Whereas this is having good dynamic response. Means dynamically it will be able to show you what is the reading. Doesn't take much time. The load should be perfectly axial load. You put any angular load or eccentric load, of course you know from your strength of material subject or engineering mechanics subject, if the load is given at axially, it has different effect on the material. If you give angular or you give eccentric load, there will be a moment also along with the force. So moment also will have an effect on the material. The deformation will be different. So while applying, the load should be properly applied. Have you seen people telling, hey, don't stand in the corner of the weighing bridge, small, even human weighing bridge machine also. You cannot put one leg and then, the one corner you balance yourself, the weight may be slightly different from the back. You have to properly stand with two legs properly like this and see, you will have consistent reading and correct reading. Have you experienced this in weighing machine, weighing your own weight? That's because you cannot put an eccentric load on the weighing machine. Today 4 hours. If you sleep, you will lose 4 hours. Take notes so you can avoid sleep. Overloading may permanently damage the strain gauges. Okay? Because strain gauges are very fragile devices. I had a few samples, but last semester MTech students were asked to do weighing bridge using strain gauges. Many of the strain gauges were spoiled, not used in handling. During the soldering process, strain gauges were spoiled. Very thin, very soft strain gauges. Each one may cost only 60 rupees, 70 rupees. We bought it from Pune. But the grid, if you put overload, slightly put extra load than what it is meant for, cut off, then no change in resistance will be there. It will have a disconnection. Okay, after that it will be used. You will use this. Weighing bridges, tool force dynamometers, they're all applications where you can use. Right. Next device for measuring the force, almost using either LVDT or strain gauge, is the proving ring. So what you see in front of you is proving ring. This is a proving ring. Okay. This is a proving ring. It's written proving ring. This is the elastic member. Here we have a dial gauge. A dial gauge is used to measure the deflection. In place of that, you can put a strain gauge on sides. You can put one LVDT in the middle instead of a dial gauge. And this is for applying force. When I am rotating in clockwise direction, what will happen? The ring is being pushed downwards. That means compressive force I am applying. It is firmly fixed. Suppose I am rotating in the anti-clockwise direction, what happens? It is being pulled up, so tensile forces are. A simple mechanism for a demonstration to the students. It's a strain gauge. Okay. You see that when a thin elastic ring is subjected to force, it deflects. The deflection is proportional to the applied force. By measuring the deflection, you will be able to measure the force. So when you apply force, there is a deflection. What is perfectly circular will become slightly oval. Oval means it will not look like egg shape. A small compression will be there. That you should be able to accurately measure, calibrate it to the amount of force that you have applied. Then from the deflection, you will be able to measure what is the amount of force that you have applied. This is 20 kilonewton force. Up to 20 kilonewton force, you will be able to measure using force. So this is the proving ring, and this is the force applying mechanism. Here we have a simple screw jack mechanism, so where you can simply rotate this and apply force. So this is the ring that we shown here. Now, same strain gauge 1, strain gauge 2, strain gauge 3, strain gauge 4. Wherever there is you apply force, what is seemingly a circular in shape will try to become elliptical in shape as it comes down. Let's say this is fixed and you are applying force here. This becomes elliptical in shape, isn't it? During that time, strain gauge 1 and strain gauge 3 will be subjected to tension or compression. Wait. Strain gauge 1 and strain gauge 3. I think you have to check your eye doctor.
No, sir.
Huh?
It has become elliptical.
Elliptical. So outermost surface will
Compress.
You get
something
stretched.
like this. You see, my hand, it is like this. Here
Stretch,
the skin is not stretched. Whereas as I fold, what happens to the skin here? That gets stretched. That means they are all undergoing tension. Look at the skin here. Now it is stretched. You see a better color actually, one shade better. As you come closer and closer, the shade becomes dull. Why? It's getting contracted. So inside it's a contraction, that's compression, and outside it's expansion. So you put 1 and 3. You remember 1 and 3, R1, R3, the positive activities, positive strain, there is a change in resistance in the positive direction. 2 and 4, there is always, here already it is a negative quantity. There is a reduction in from the original value. So delta R in 2 and 4 will be a negative quantity. Put them in negative values. So negative of a negative value will become positive. That's the idea. So whatever is the strain proportional to that, 4 times the delta R you will get. Here delta R1, R3 directly you will get from here. R2 and R4, it's a negative value because of the compression here, and the compression value again minus of minus value will become positive. So it is delta R1 plus delta R2 plus delta R3 plus delta R4 divided by some R. Assuming R1, R2, R3, R4 initial values are all same. So here it is R and 4 times of R. 4 and 4 will get cancelled. E divided by R into delta R will become the unbalanced voltage that you get. Okay. So that's how you measure the strain using proving ring. This is for overload protection. Here what happens, suppose I ask you to operate this. we bought little overweight because it will not be spoiled. We have one more proving ring setup which is spoiled by our students. Suppose you ask you to apply force, simply people show their strength. There are some gym body people. They go to gym here, they do the they turn. What will happen to the proving ring which is in the bottom? Gone. Okay, and then we don't want such thing to happen here. Of course, in the laboratory setup we have loading mechanism like this. In industry or in application area, suppose we have a weighing bridge, we can measure up to 10 ton. We have or 20 ton capacity we can measure using loading set. One lorry driver is coming to measure the weight of the content in the lorry. He himself doesn't know what is the weight. That is why he is coming to weighing bridge for measuring, isn't it? Whereas my weighing bridge can measure only up to 20 kilonewton. So 20 ton, TON. Ton means 1000 kg. 20 ton means 20 into 1000 is something. Okay. So I loaded my vehicle fully. I don't know what is the weight. Simply come and stop it in the platform. What will happen to the strain gauge? I mean the cell that is inside gets damaged. We don't know. We don't want such action to take place. Okay, we want to protect it. So people have designed a mechanism by which you can safeguard the proving ring. This is the elastic member which is sensitive to the force, which is critical for the operation of the proving ring. Okay, now people have designed the proving ring like this. So what we'll do, up to the force limit for which it is designed, the force is applied, the gap will keep on reducing. Of course, here also that circular nature becoming elliptical, all that will happen on the sides. There is no difference in the operating principle. Only thing, the gap keep on reducing till the limit up to which it is designed for. Let us say 2 ton is the limit. Once it reaches 2 ton, this gap will become 0. This will start touching each other. This will start touching each other. Then any extra load that you apply will get directly transmitted like a shaft. Like a shaft. Nothing will happen to the proving ring. Nothing will happen to the proving ring. It will act as a shaft and just transmit the force to the downward. There is no elastic member in between. There is a minor, small portion of elastic member. This is actually drawn by me. That is why the cross section looks a little small. But in real case, the cross section of the member which is above and below, and here elastic member will be same. So it looks like acts as a column, simply transfers the load from top to bottom. There is no change in the force. So this is the proving ring. Is it clear to us? This is the force applied to proving ring. Proving ring, you get deflection. The deflection can be measured using, see there is a dial gauge there. In place of that you can put a LVDT, which I have explained yesterday, or you can put a strain gauge on both sides and measure any way that you can measure using proving ring. And you get these are all specifications we got. Accuracy is very high, measurement range is very high, resolution is perfect. Of course, hysteresis is a bit low here. Very sensitive to stay magnetic EF if you are using LVDT type. If you are using dial gauge type, that's no electrical output. If you put strain gauge type, there is a temperature problem. So any displacement measuring device, it has its own pros and cons. Accordingly, piezoelectric load cell, the working is very straightforward. You have piezoelectric crystal. You apply force on 2 parallel sides. The charges are developed proportional to that on other 2 parallel sides. Then top and bottom plate, if apply force, side 2 parallel plates, charges will be developed. Okay. So put the electric connector, take the electric charge, amplify it. That will be proportional to the applied force. Straightforward. That effect is called piezoelectric effect. Principle is straightforward, used for piezoelectric force. The specifications, advantage, very rugged. Natural frequency is very high. So natural frequency is very high means resonance will not happen. If resonance does not happen means your measurement error will be less. You will not get any erroneous reading at that particular frequency. What is the problem of natural frequency? The frequency with which you are applying the load and the natural frequency of the component, if both are same, then resonance happens. That means it starts vibrating itself more in very high amplitude, which leads to error in the measurement. whereas natural frequency is very high, then the application of load, the load frequency is less, then resonance will not happen. You avoid the resonance, so that you will be able to reduce the error because of the resonance. Dynamic response is very good. Electrical output you will get, and high frequency, high frequency. There is a problem with temperature and hysteresis error is there in the piezoelectric. You apply force, remove the force. It is not that you apply force, it gives charges. You remove the force, immediately it comes to zero. It takes some time to come to zero voltage. That's called the stray EMF or stray charges. That leads to hysteresis error. That problem is there in any piezoelectric related sensors. So far, what we have seen is force measurement. This is a torque measurement. Here you have a force. This is a radius. Force times radius is torque. So you have a torque measurement. Either we wanted to measure the power. Power means power transmitted through a shaft. So what do? We wanted to measure the speed as well as torque. Apply it in the formula 2 pi nt by 60 to find out the power. So there we wanted to measure the torque. Other cases like in assembly units, I have a pneumatic screwdriver or electric screwdriver. There is a plastic part which I need to assemble. For example, there are screws here. See, there are screws here. This plastic can take only so much Newton meter torque. While screwing, if I apply more torque, it is a self-threading. If you apply more torque, simply it will rotate one more rotation, the thread will come out of it. Thread will come out of it. The threading process is spoiled completely. So measuring the torque in such instruments or measuring the power, torque measurement becomes important. Also in viscometer, we measure the torque in order to measure the viscosity. That's a measuring principle. We basically measure the viscosity, but actually we measure torque in order to measure the viscosity. Stroboscope type, proximity torque type, strain gauge type, optical torsion type. They are all 4 types of torque measuring instruments. We will be talking about only strain gauge torsion meter because that is there in your syllabus. Other things are not there. Anyway, other things I have discussed in the video that's available in the network. You can also go to YouTube and. When a shaft is subjected to torque, it is twisted. It is twisted. And the strain takes place in the principal axis direction. How many of you have gone through strength of material subject? Sir, I have studied strength of material subject. Anybody have not studied? 1 or 2? Okay, fine. So whenever there is a twisting action, the maximum strain will be in the principal axis direction. So that will be 45 degrees to the axial direction here. So this is the direction and this is the direction in which maximum strain takes place. Maximum strain takes place. These are all called principal axis. Okay. So what do? We want to measure the strain and calibrate the strain in terms of torque. Put the strain gauge as there, connected to strain gauge, measure the strain. Amount of strain is proportional to torque, so you calibrate it in terms of torque, you measure it. Nothing. Okay. The problem in strain gauge measurement, especially in a rotating shaft, is the rotating, for example, a motor or a fan. I put there's a shaft, put a strain gauge is measuring the change in resistance, put a Wheatstone bridge as well, maybe the power also, a battery inside the shaft itself. I want the output to come out of the shaft is rotating. I cannot connect a wire. Along with the shaft, the wire also will get bound. I don't want that binding action. I want only the signal to come out. So what do? Either we will use slip rings. What is shown in blue color is a slip ring. That means what? A copper ring on the mild steel rod. There are 2 rings, one ring, other ring. And a brush will be touching that ring. That will not move left side or right side. It is constrained to touch only that particular ring. That ring, you give one electrical connection here, one connection here, another connection here. So both electrical output will come. Shaft alone will be rotating. This will not rotate. It will always be touching. The brushes will be touching the slip rings and electrical connections. Okay. That's the one problem in a rotating shaft that we have. Either you can use that technique or transformer principle. Transformer principle, yesterday we have discussed. What is that? From primary winding to secondary winding, the mutual induction takes care of the responsibility of transferring voltage. So due to mutual induction, the power supply is transferred to the Wheatstone bridge supply, and there is an unbalanced voltage that's coming out, that is taken out from here to here. This will act as a primary winding, this will act as a secondary winding, and take out the change in voltage proportional to the change in resistance, and so much voltage will be induced here, that take out and do the remaining signal processing. Calibrated in terms of torque will be able to show that. You are able to understand the problem. In rotating shaft, you have to take the electrical signals out. You cannot connect a wire directly to a rotating shaft. The shaft will get. You have to place the strain gauge on a rotating shaft, but signal alone should come out. Two techniques. One, slip ring technique, as we discussed here. Other, the transformer principle, so that we will be able to. The other, you use a transformer principle to take the signals out of the. So this is the first lecture.